Modern computers do this 27 trillion times faster, and this has been achieved in a mere 79 years. According to scientists, the power of computers will grow several million times more in the next 100 years. It's hard to even begin to imagine what kind of world our children and grandchildren will live in. Already, virtual worlds like the one, for example, in Grand Theft Auto, shock with their detail. It's easy to imagine that they will become indistinguishable from reality in the next 50 to 100 years. In fact, it's possible that we will be able to create virtual universes in which the characters really think and have minds similar to ours, but won't know that they live in a simulation. This is frightening on many levels. And what if we are such characters already? What if the whole world that you see outside the window is a simulation? Philosopher Nick Bostrom first introduced the general public to this hypothesis regarding the virtuality of our world back in 2003. Its essence was that if many technologically developed civilizations exist in our universe, then it is likely that they can create simulations similar to those in which you or your children play sitting at your computers, only millions of times larger and more realistic. This means that you or I could be in the role of an NPC, a non-player character, in some alien sandbox right at this moment. And people really are taking this seriously. Elon Musk, for example, said in 2016 that there's only one chance in a billion that our reality is not a simulation. When you hear such a thing from somebody like Elon Musk, serious doubts regarding the nature of our reality begin to arise. This forces us to at least begin a serious search for some kind of answers. And this we will do now. Evidence of our virtuality. Grand Theft Auto 5, also known as GTA 5, is a very good example of how all this could be accomplished. In the game, on one of the many streets of its virtual city called Los Santos, you see a very familiar picture. You are surrounded by cars that are hurrying to and fro somewhere into the distance, and crowds of people line the sidewalks. In general, everything's very similar to how it is in real life, and more crowds of passers-by. So, being on that Los Santos street, you might think that the same story is happening to others, that life is alive and happening in the whole city at any point in the urban landscape. But, in fact, this is simply not true. You must not forget that everything you see is just an illusion, built just for you. While you are on the street with the conditional name A, absolute nothingness has filled Street B. Nothing happens there. The game continuously, magically draws for you this living, active life, while Street B drowns in silence and, in fact, barely exists. All modern video games work on this principle. When you are absent from a certain location of a virtual city, there is absolutely nothing at this location. No people, no cars, no city itself. The developers optimized the game in order to reduce the load on the computer hardware. Thanks to this, you can enjoy such incredibly realistic graphics and in-game physics that are the modern masterpieces of the gaming industry. If a player, or rather a character, turns and looks at something, the computer makes the image in front of him as detailed as possible, and the textures and objects behind the player's back, that is, out of view, become as simple as computationally possible, or really disappear altogether, except as a potentiality. As we said, this allows the computer to reduce the load on the game platform while maintaining beautiful graphics. If you look at the location from on high in GTA 5, the whole city will look as if it is in the palm of your hand, and you will see how cars are rushing up and down all of the numerous streets. So, does that mean the power of the console works that are far from the observer? If we fire a rocket into such distances, we can barely see it explode. If we fly closer, then the explosion looks much more detailed and realistic, and requires far more computer power. The next example is the game Civilization 5. If you quickly move the camera from one end of the map to the other, you will see the location loaded right before your eyes. The game engine is not perfect, so we can see how the view responds to our actions, realizing that we are looking at it. That is, the observer influences the game world by the very fact of his or her observation. This is how any video games of the future will work as well. Even if super powerful computers can simultaneously calculate all the more or less large objects in a large location, even over many years, small details will remain to be rendered. Flies, blades of grass, and yes, even microbes, of which there are quite a few, all of which will be loaded only under the gaze of the observer player. Everything is for the sake of optimization. So, after that gaming preface, we now move on to the first proof of the theory that we are living in a matrix-like simulation. You may know about or remember one of the most famous experiments in the history of physics, the experiment of Thomas Young, the double-slit experiment. It was a real coup in physics and led many scientists into the study of quantum mechanics. If you throw solid balls at a shield with a slit cut into it, a single diffuse strip designating the strike points will appear on the screen behind the shield. If there are two slits in the shield, then there will be two strips. But how will waves behave if aimed at the shield? They will pass through the slot and spread out. The greatest impact of the waves will be in the line of the slit, as in the case with the balls. But if you add a second slit, everything changes. A number of alternating interference strips will appear on the projection screen. And when we shine light on the two strips, this is exactly what happens. And this is how Mr. Young proved the wave theory of light. If light were corpuscular, like a particle, instead of wave-like, it would behave like the balls, and the screen would show two strips of light corresponding to the two slits. That didn't happen. Later, it turned out that electrons and protons behave exactly the same way, showing that they also seem to exist as waves and not as points. There was one assumption that perhaps light and the others were particles and that somehow the particles bumped into each other and flew apart. So, to test this, physicists decided to shoot electrons at the target one by one, single file. And what do you think happened? The strangest thing imaginable. The interference pattern still appeared on the screen. It seemed that the single electrons somehow divided into two waves, passed through both slits, then interfered with themselves. Impossible. So physicists tried to find out through which gap the electron actually passes. They installed measuring instruments to check this. Another seeming impossibility occurred. The electrons stopped behaving like waves and began acting like particles, and left a trace on the screen of two distinct strips with no interference. They had to admit something completely mind-blowing, that the fact of our observation or measurement destroyed the wave function of the photons, causing them to become like points, corpuscular. The electron, under the influence of observation, behaved like a particle, flying through one slit and not through two. Interpretations. Well, it certainly looks like the work of a game engine, doesn't it? This might make you think that our world is running like a game on a computer. The computer's power is not enough to calculate the motion of each and every particle, so it uses a simplified model and applies precise calculations only if an observer needs to look at the particle, so as not to break the illusion of the reality of the world for the observer. Such an explanation could not have occurred to people from the past. The results of Thomas Young's experiment were published in Hagen Interpretation, was proposed in 1927. Niels Bohr and Werner Heisenberg suggested that elementary particles are both waves and particles. To measure an electron, it is necessary to strike it against the screen of the measuring device. The wave functions of the electron collapse when it is measured, and it becomes only a particle. And this means that it is not exactly the observer, but the measuring device that influences the result of observation. But if this theory is correct, it still does not discount the hypothesis of the simulated matrix world. For example, a programmed photon could propagate in the network as a wave and restart when the node is overloaded, turning into a particle. This way, one can explain both quantum waves and the collapse of the wave function. The second most popular explanation of the behavior of particles is the many worlds interpretation. To greatly simplify, it looks something like this. We can assume that there are parallel universes in which the same laws of nature operate, and for each act of measuring a quantum object, the world splits into several versions. Each of these versions sees its own measurement result and acts according to it in its universe. In the eyes of the layman, this is a strange explanation. But it's a free world, at least we think it is, and so anyone can decide which interpretation they like best. 8 for the many worlds theory. Several other scientists chose other, less popular options. And 18 part slit experiment, this time with a deferred choice element involved. In simplified form, it goes something like this. Particles are again shot through a barrier with 2 slits in it, but this time the observation of which slit they pass through is made at a time when the particles have already passed through the slit, but have not yet hit the projection screen. Like an observer who only opens his eyes after a certain moment. And can you imagine this? The electrons behaved like particles at this moment, as if nothing had happened from the moment of their launch from the electron gun, as if they did not pass through both slits and did not represent a wave. It seems the particles knew that they would be measured before it ever happened. The second proof. The next hint at the existence of a matrix can be arrived at from the maximum speed in the universe, the speed of light. Einstein explained that nothing could move faster than photons in a vacuum. The speed of light is a limit and a constant. Additionally, the faster an object moves, the more time slows for that object. At a speed of 300,000 kilometers per second, time stops altogether. That is, you could get to distant galaxies, let's say 3 billion light years away, so time for a photon stands at 0. It cannot accelerate faster. For this, it would have to slow down time even more, which is impossible as time has already stopped. But why do speed and time have such a relationship? Why are space and time interrelated? The answer suggests a virtual world. The matrix hypothesis assumes that the speed of light is a product of information processing. That is, the world is being updated at a certain rate. It's 1 trillion times faster than any of our supercomputers now, but the principle is the same. Time slows down with an increase in speed. Because virtual reality depends on virtual time, each processing cycle is 1 tick. When the computer slows, the playing time also slows down a bit. This is very similar to the way in our world that time slows down with increasing speed or near to massive objects, which points to the possible virtuality of our universe. It can be assumed that in a ship that rushes with tremendous speed, the processing cycles of the system hang for the sake of saving resources. The third piece of evidence. The most serious proof that we live in a matrix simulation is quantum entanglement. Well, what is it exactly? A photon flying through space can be considered to be rotating. That is, it has something called spin. In fact, photons don't really rotate, but this is a simplified model. So, physicists believe that, most likely, before a particle is observed, it does not even have a specific spin. That is, no one is looking at the photon yet, so it cannot determine which way to turn, and is considered to be in a superposition of uncertainty. It would seem that it's difficult for nature to calculate the rotation of each and every particle, and so it uses a simplified scheme for this. But, again, when an observer appears, the particle becomes physically more complex and more real, and its rotation is calculated. An experiment was proposed by Albert Einstein, which was to test the Copenhagen interpretation for strength. Some very interesting results were obtained from this experiment. The essence of it goes like this. If an atom, for example, cesium, emits 2 photons in different directions, then because of the law of conservation of momentum, their state will be interconnected. If one of them rotates from the bottom up, then the other will rotate from the top down, always. They will always have spin in opposite directions. This is called quantum entanglement. But remember, the photons do not know which way to spin before they are observed. So in this case, if the fact of observation made one choose one of the options, its tangled partner must then immediately have a spin in the opposite direction. That is, by the very fact of our observation of one photon, we affect the spin of the other photon, even though we did not observe the second photon. And the second photon is required not only to find a spin, but to do so instantly, even if the photons are at a great distance from each other. That means that if the entangled photons were somehow sent even to different ends of the universe, this information about which way it should be spinning should somehow fly or jump across the universe to its partner at several quadrillion times faster than the speed of light, so that it basically instantly gets its spin. This is incredible. It violates the very laws of physics as we know them, because nothing can move faster than photons in a vacuum. However, the second photon still manages somehow to get this information in zero time. But how? How does the partner entangled photon learn with such speed that a colleague was observed, and so know to spin in some particular direction? Einstein was convinced that such an instantaneous connection was impossible, and he assumed that when entangled photons emerge from the atom, they already contain information about the past and know which direction they will rotate if or when they are observed. That is, the observer does not change things but only recognizes the spin of the particle. But 17 years after Einstein's death, it turned out that this singular, unparalleled genius was mistaken in this case. That's right, Einstein was wrong. To prove the presence or absence of information about the direction in which the particle rotates after observation, Irish physicist John Bell set up a very complex and ingenious experiment. The results were astounding. Bell proved that the entangled particle does not have a clue before it is observed in which direction it will spin. The photon randomly chooses a spin only after measurement. And this is proof that entangled elementary particles can transmit information to each other much faster than the speed of light. The experiment gave us more new questions than answers. In 2008, a group of researchers from the University of Geneva decided to clarify the speed of information exchange between entangled particles. They were able to separate from each other two entangled photons at a distance of 18 kilometers. They measured one particle and recorded how fast the second reacted. It turned out that, as measured, the photons somehow were able to transmit information at least 100,000 times faster than the speed of light, and maybe even instantly. Perhaps Einstein was right when he said that instant communication in the physical world is impossible. But if we substitute a virtual reality in place of the physical world, the instant connection is easily explained. When two photons become entangled, their programs are combined to jointly see the 2 points. This combination of programs will respond for both pixels, if we can call them that, no matter where they are. At the moment of measuring one particle, its program randomly chooses one of the spins, and the program of the second immediately reacts. It becomes clear why the distance isn't important. The processor does not need to go to the pixel to ask it to spin, even if the so-called screen is large, even as large as a universe. Physicists say that no one really understands quantum mechanics, but if we assume that our world is virtual, everything quickly becomes quite clear. To describe the world of elementary particles and their interaction, scientists use quantum mechanics, and for the macro world, Einstein's general theory of relativity is used. But if these two worlds coexist in nature, then a theory must exist that would allow for both. And this is exactly what the hypothesis of simulation does. It perfectly explains this. The mysteries of the Big Bang, the curvature of space, the tunnel effect, dark energy, and dark matter all can be explained on the basis of the assumption. They say this simulation theory, even if confirmed, wouldn't change anything. But official confirmation could strongly spur new research, and perhaps scientists would be able to find new shortcomings in our world, and they could be used to create new technologies. For example, if quantum effects are caused by the virtuality of the universe, the creation of quantum computers or quantum cryptography can be called the use of the conventions of our world. Are we in a matrix? New, indirect hints that we live in a matrix are discovered every year. At such a rate, in about 30 years, the virtuality theory of our world could become as official in the world of science as the theory of evolution today. Perhaps it won't be too long until they teach in schools that we live in a virtual world. although it is somewhat demotivating, realizing that you might be just a complicated program with feelings and self-consciousness. Elon Musk believes that, on the contrary, it would be good news. The simulation hypothesis solves the Fermi paradox and shows that intelligent civilizations are able to avoid self-destruction and technologically grow to achieve even the creation of virtual worlds. So, life in the Matrix for Mr. Musk is a pretty decent utopia. He wants this to be true. By the way, recently the famous scientist Neil deGrasse Tyson and some of his colleagues spent several hours debating the topic, is the universe a computer simulation? Be sure to watch it. If you like this topic, I advise you to see the film The 13th Floor and, of course, the Matrix trilogy. And don't forget to put likes and subscribe to the channel. Otherwise, Agent Smith will come knocking on your door very soon. What will be if we wrap you round and round with Scotch tape? Throw the whole package into a microwave oven. Roast it quite well. Feed that to a giant hungry whale. After that, drown you in the ocean. Then bury you alive, send you into space. Then let you drop back down to Earth straight to the bottom of the Mariana Trench. After that, take you out and dry you under a nice warm lightning storm. Dress you up, comb you out, stick you on a plane, climb to a height of 30,000 feet, and toss you out once more, where you plummet back down to the onion. To explain, just click on the link in the description and watch the first episode in this awesomely great new cartoon series, soon